Okay, darlings. Monoprotic, diprotic, and triprotic. You should be able to tell me an example. First of all, what the heck does mono, di, and tri mean? What does it mean to be protic? And then what is an example of those? Pretty readily, okay? Allie, mono, di, and triprotic acids. What's the difference between each of these? Has three what? Hydrogens, right? It's protic, right? Protic sounds like proton, right? Well, in the acid-base world, proton is the same thing as hydrogen ion, because hydrogen ion has lost its only electron, leaving inside the nucleus and the atom itself nothing but a proton. So these are 1H, 2H, 3H acids, right? So Evan, tell me one example of each.
Hydrochloric acid.
Okay, so hydrochloric acid is monoprotic. I'll come back to you. Alina. Sulfuric, so H2SO4 would be sulfuric acid, that's diprotic. Madeline, you have a triprotic one? So what's the name of that? Phosphoric acid, right. So as long as you can detect the H, and you can see 1, 2, 3, you can determine it's mono, di, and tri. What if I told you this one? I'm going to write 2 up here, okay? What protic acid are those? That's not an option. So here, you see that quad protic acid is not an option, right? So mono, di, and tri. So what would those be? Those have to be mono. This is the point. Anytime we're dealing with an acid, there's usually 1 to 3 H's that are acidic hydrogens. Some of the hydrogens just make up the polyatomic ion, right? They're not actually the acidic ones, the ones that pop off to make the H free. The H plus is free. So this guy is what? In red here. That's acetic acid, right? Or that's acetate, which is making acetic acid. It's this H right here that's the acidic hydrogen. This is most of the time what people get wrong, like on the multiple choice test, okay? This one's the acidic one. And so if that's the acidic hydrogen, we call this monoprotic because it's only that hydrogen there that's going to force the ionization and then hence the pH to drop and so forth. So notice C2H3O2, H. How many H's total are here? 4. How many here? 4. How many C's here? 2 and 2. O's, 2 and 2. This is the same thing as this. I've written it in a structural expanded form. So CH3, like this. C, there's a C right there. Double OH, and this is called a carboxylic acid. Like that. This is how it looks. These little dots and everything. So this is acetate with a hydrogen on the side. So boom. Can you see acetate? C2H3O2. And this over here is that hydrogen that we were just talking about, is the acidic hydrogen. So I like to give you both expressions of it because most people can't identify that they're the same thing. Both those are acetic acid, both of them are monoprotic. This is a weak acid though because it's not one of our 6 strong. Cool? Okay. And so like we draw those little structures a little bit more complex in AP. That's what they're kind of fun. One of those was on their AP exam. Sorry, my phone's not on silent. Okay. Hydrochloric acid reacts with sodium bicarbonate. Abby, start me off. Okay. Brandon, finish. H, say again. Hold on. I have so many who were just fell and died back there's okay. Okay. So I hear. Let's pause for a second. You guys okay? Okay. So let's pause for a second. This is just a double replacement reaction. This is an acid and a base. The base in this case is not a traditional base. It's actually the bicarbonate ion is basic. If this is baking soda, it will neutralize an acid. It doesn't look like a traditional one. So let's go ahead and put our pluses and minuses underneath where each of the cations and anions are. Okay. So the H here is going to bond with what? Bicarbonate, right? So it's going to be HCO3, but HH looks stupid. So let's just write it H2CO3. Okay. And what else goes together? NaCl. Okay, so now that makes a little bit more sense because and most of the time we do an acid plus a base yields a salt plus water. Now this one isn't water yet, but wait. This is carbonic acid. Carbonic acid is what actually makes your soda bubbly. What's the bubble made of? Carbon dioxide. Okay, so if this guy, H2CO3, breaks off into carbon dioxide, it must also make something else, water. So that's why this actually still is an acid-base neutralization reaction, because it does still make water. Not immediately. It's a secondary reaction. It's like an afterthought. But it does still make it, and it does make a salt. So acid plus base yields salt and water is a neutralization reaction. What's a hydrolysis reaction? It's the opposite, right? Because it has to use water to force salt apart. And that's what your lab is on. We'll get there in just a second. Let's go ahead and do one more of these. Which one do you guys want to do? Okay, I'm going to choose for you. Calcium hydroxide, acetic acid. Sorry, that's the one I really want to do. This one's the one we've not seen yet. Calcium hydroxide. Avery. OH. 2, good, because the calcium is a 2 charge. Reacts with acetic acid. Alina, what's acetic acid? Okay. And it's nice to put your pluses and minuses if you need it. Sometimes you can just see it. So Jasmine, what would be one of the compounds made? Ca and then acetate, right? C2H3O2, and then what would be the subscript here? 2, because calcium's got a 2 charge, drops it down. Acetate has a 1 charge, so it crosses over as a 1 right here. And then Eli, what would be the other one? So we just did calcium and acetate got together. And the things that are left are our H here and our OH here. So what are they going to come together to make? Well, that's going to be you just putting the 2 together without thinking about your cation and anion. So we're going to put the cation first. So the H plus comes first. And then the OH right here, which is a minus charge, comes second. So that's HOH, which for us is just H2O, which is water. But we do need to balance it. So I like that you put the 2 in there. We need to put a 2 we need to balance it by putting a 2 in the front here, and that distributes out to the OH and to this H, meaning we also need what? Anybody? 2 in front of the acetate, right, or the acetic acid. Okay, so neutralizations always generally make salt and water. Hydrolysis usually takes the salt and water, reacts them to reform acids and bases. So let's get a piece of paper out for hydrolysis lab. I'll probably give you guys about 40-ish, 45 minutes for that. It's a really easy lab, and I want to make sure that you're clear on what to do before we move. We went over for our Monday, actually, weekend. We went through how to determine that the ending solution when a salt and water together, I was like, hey, a salt can be acidic, a salt can be basic, or a salt can be neutral, and you're going to actually test the pHs of these solutions to determine if they're acidic, basic, or neutral. You're going to be using litmus paper. So my joke up here, hey, litmus paper, I said blue. Basic humor. Basic. Red turned blue. Remember my dance? Red to blue, base. No. Blue to red acid. Yeah, blue to red acid, because it totally rhymed, because it was they both end in D. Okay. So, and whenever you're determining if the salt itself is acidic, base, you're going to really need to first test the pH of those sample you make. And then remember that we talked about how acids and bases, how a salt was made. That's an acid plus a base yields a salt and water. So I like to call them baby salt. Comes from parent acid and parent base. Okay, so mom and dad base, acid and base make baby salt. So these two control the acidity level of the salt made. And so that's what you're going to see. You'll see that language on your lab sheet itself. All you're going to do is put just about the size of your pinky nail. Okay, it says to mass out 0.5 grams. Ain't nobody has time for that. Get a little scrupula about the size of your pinky nail. Drop your salts into water in your test tubes. Dip a stirring rod inside the test tube, because if you put litmus paper down there, it's not coming back out. Right? It's going to be in the very bottom. So take a string rod, stick it into the test tube, dip the string rod into the solution, take it out and dip it onto your litmus paper, and it will change color. That way you don't get the litmus paper stuck into the bottom of the test tube. Okay? Okay, so small groups, let's do groups of 3 or 2 or 3. Let's go back and I'll show you where everything is, and we'll be back here together. You do need goggles, but if you have open-toed shoes, you'll be fine. Everything's going to keep your toes. Yeah. Don't put it in this stage. It's fine. Fine. Hydrolysis of salt lab. Hydrolysis of salt lab. Alright, so let me give you some orientation. Ignore this stuff. It's not done yet. Ignore this. But at the station here, I have sodium chloride, sodium carbonate, sodium acetate, and ammonium chloride. I have them here, and I have them right here in front of this group. Right back here. And I have 4 of them without they don't have mixed in. But I have 4 sets. So just make sure when you come over here with your scapula, 1 scapula for your group, you're just going to have to wipe them off in between. You're not contaminating cross-contaminating. And like I said, it's not an actual measurement. It's about the size of your pinky nail. You're going to put it in water. Okay? This won't take you guys very long. And the litmus paper should be at your stations. I'll get you guys. You only need, if you take the litmus paper, you can actually conserve it by ripping it in half, because you don't need all that litmus paper just for a dab. So if you rip the litmus paper in half, you'll be able to see.
What did you get? What did you get in the last?
Hydrolysis.
It's cool, yeah. Every ladder. Right. Point to yeah, me too. You've got you need more. I need for one of us. Get a stir. What's the next one? Yeah, the first time you gotta get confused. And then I was like, spinning. You gotta make it. Look. See? Now it's like a you gotta make it smaller. We had maybe. First, we're gonna copy this thing. We should probably do it. Last one. Yes. No.
guys, how's it going? I'm like, teaching England's class and y'all at the same time. Yes.
She doesn't like
Give me another one.
I want to hurt my Oh, that was real. You missed those. All right, that was stir fry. No, hey. So Evan, this is how that is sodium carbonate. That was this is amazing. I know. You gotta do the blue. Oh, it's blue, red, plastic. Oh, yeah. You did that. You did it. Right now. So, you guys great.
Actually, blue.
Yeah, but if you look at it, it's like
Technically, water.
technically water. I mean, it kind Alright, this is the second one. Ready?
Over here.
Ooh, that's good. Maybe the blue. Maybe the blue. That's a big. Maybe we need to do two more. Alright, this is sodium acid, right? Right. That's a new one. There's nothing.
I think you have to. Oh, she said you can split on it now. Yeah, give us.
Yes, no, not it.
I'll do it.
Cover.
What'd you do?
And then, I don't know what that is.
Nothing changed. Oh, this is the sodium.
Sodium acid.
What do you see? Look at that. Away.
This is ammonia.
Yeah.
There's a tornado, people. You can't move
Oh my
it.
God.
There's a tornado. Don't have your cover. I love them.
Right? Ready? That's sodium chloride.
So wait. So. What is it? Right? That is the red thing. Water. What is that?
Sodium chloride and sodium carbonate.
Yeah, just bring it.
I know ammonium. Sodium chloride. Would you guys have thinking? It's not the first one.
This one's blue. And the last one. Alright, I'm going to ask, has everybody collected all their data? Okay, continue collecting your data. But let me do a quick example of how to accomplish this chart. Alright, give me your attention in 5, 4, 3, 2, 1. Thank you. First sample you put in there was sodium chloride. I think we all know the formula for sodium chloride is what? NaCl. Okay, so NaCl got added to water. It's in the form of HOH. I'm writing it that way because I think it's easier for you. I guarantee you'll like it once you start to see the magic. Na gets with who? OH. So that'd be NaOH. H gets with Cl. Okay. So we got our formula. Tell me the names of these, Trinity. Sodium chloride plus water yields sodium hydroxide and hydrochloric acid. Okay, so we can say the words. We write the words for the word equation. That's all that means. So you'll put sodium chloride plus water yields hydrochloric acid and sodium hydroxide. So you're using your nomenclature. This is a practice, right? And then your blue litmus paper from this one should have, what happened? Nothing. You say nothing, but you mean it stayed blue, right? So the blue litmus paper stayed blue, and the red litmus paper stayed red. If you got different results for on sodium chloride, you mixed up your samples or you contaminated something. So if they both, so the first one's like, hey, I'm a base, right? Blue base. Red acid, okay? That's what we think. But then you're like, you can't be both unless you're water. So what is the pH of this sample? Neutral, okay? So that's what you should expect. In a couple minutes, I'll go over the litmus results for the others because you should be able to continue from there. Please do not waste your time. Oh, the acid member and base member. Sorry, that's what I was supposed to do. Acid member and base member are the people in the back. Please hush. Thank you. If this baby salt was previously made by two components. Remember, salts and water, they come from acids and bases, right? The neutralization reaction they just did for warm-up. A plus B yields salt and water. We just reversed the process, right? So this is the base, and this is the acid that made baby salt. So this would be considered the base member, and this would be considered the acid member of the salt, or parent acid or parent base, or acid member, base member. There's two different terminologies. But you're just looking for the acid and base made, and those are the what you'd identify in your chart as accordingly. Okay. I think you guys got it. I'm going to give you guys about 15 or 20 more minutes to accomplish this entire task. Thank you. Leave it there. I'll get it. That's probably you guys, not that. I'm quick. I'm quick. You gotta be faster. All right, lovely people. Let's recap the couple of questions I saw were left blank on PS 19A. The one that, well, I took off some points based on either completion or something like this. Magnesium hydroxide does have to have parentheses around the hydroxide, and it should be on the outside, not on the inside of the parentheses. That's a really easy one that you just probably learn pay attention to. That was one of the very first ones. Phosphoric acid, H3PO4, not H2PO4, so the charge of phosphate is a 3. That was another nomenclature catastrophe on some people. So those are easy ones. Just pay attention, know your polyatomics, charges and all, right? The other one was 13, which asked about the weak acids, right? So how do you find the pH for weak acid? If it's a strong acid or base, how do you find the pH? If it's a strong acid or base, how do you find the pH? Or how do you, sorry, let me rephrase. If it's a strong acid or base, how do you calculate the pH? So you calculate with it. Yeah, you actually calculate with this equation. pH is equal to negative log of hydronium. That's only if it's strong. If it's weak, you actually have to do something called an icebox. So basically, we know that whenever you have an acid, I'm just going to call it, let's just do, we'll do nitric acid. No, I'm going to do a weak acid. Okay, acetic acid, C2H3O2. Whenever it adds to water, what is this acid going to do with water? This is like an example for number 13. It can only do one thing with water. It's got to be bad, people. What's bad mean? Donor of a proton. So it's got to do it. It's got to donate its proton. So what is it going to do? What's it going to make? Oops. Oh, I can move it. Oh, where'd it go? Oh, it's right there. What would this hydrogen being donated to the water makes what? Makes a hydronium, and acetate, which is left all alone with its negative charge. Okay, I've written a forward arrow here to say this is happening in the forward direction, but sometimes it actually can reverse as well. It's called a reversible reaction, two-way reaction. And this definitely reverses, because as soon as this ionizes just a little bit and it makes hydronium and acetate, it's like, oh, get back together, reform this. And so that's because it's weak and it doesn't form this very often, so it's not going to make a lot of this over here. So that's why it's reversible. So what we have to do is something called an ice box. Hi, A.P. Lang. Okay, so we have to do something called an ice box, and this is actually something we're going to go over in our next unit. Initial is what I stands for. C is change. Equilibrium. E is equilibrium. Equilibrium is our last unit. So what happens is a little bit of this ionizes. And as this little bit ionizes, we actually account for it over here and say if that's making this, this is a little bit is made. And then we actually do a little bit more complex math to figure out the pH of it. So it actually is based on the fact that it's weak on the pH in a different way. That's the only thing. So if you got confused on number 13, that's probably why it's a bit more complex. Lunch? Go lunch. Okay, number 15 was, what was the conjugates? Phosphoric acid? Is that what that was? Yeah. Okay. Some of you guys who did sulfuric acid, first of all, make sure you're paying attention there. Phosphoric acid, H3PO4. Oops. Anytime you try to find a conjugate, you always want to take whatever the compound is and add it to water and see how it acts from there. And you make your conjugate just in reference to water. It doesn't say it's reacting with anything particular. So let's add that to water. And what is this acid going to have to do? It's going to have to donate, right? Donate, donate, donate. But it's going to do that 3 times, but in 3 separate reactions. So let's go ahead and let it donate its first one. What does that make? So I hear hydronium, and what else? H2, because it's lost this. It lost one of those. So that's H2PO4, and then what's the charge over here? Minus, because once it was neutral, in this case over here, H3PO4, it's neutral, and you take away one of its H pluses, it drops the charge down to 1 negative. So now this guy and this guy, these are the conjugates over here. Which one's the conjugate acid? Right, because in this case, this acted as the acid, this acted as the base. Acids make conjugate bases, and bases make conjugate acids. Okay, so this is the conjugate base. That's conjugate base 1. And then actually this sequentially can successively ionize continually 3 times, because there's still more H's there to be dropped off. So this can be also added to water. And you can imagine we're going from H3PO4, now we're dealing with H2PO4. What's it going to become? HPO4 charge. -2, because it was just dropped to a -1, so it's going to drop further down to -2. HPO4 to negative, and then hydronium, of course. And then this one is going to be our next and final, final ionization. HPO4 2 minus, make it drop off its last H and make what? Make phosphate. So that last H gets dropped, it becomes just simply what we know and love, phosphate, PO4 3 minus. And then the hydronium, of course, still 2. That one actually had 3 conjugates. First one that formed, the second one with the H, PO4. So that was H2PO4 1 minus, HPO4 2 minus, and PO4 3 minus. That was a complex one. But does that answer any other, or do you have any other questions on case 19A? Yeah.
Number 12, can you just show us one of them? So like
12. Yeah. So this is the log of with the x, how the exponent plays into log functions. And so if you know how logs work, they're just based on log 10 or base 10. So if I tell you the pH is 3, how would you normally find the hydronium? So pH is 3. We know pH.
negative log
Or anti-log, right? Because if you know the pH, you're not finding pH. You already know it. So you do the other equation. Hydronium is equal to 10 caret negative pH, right? So log function, log rules means that 3 goes in there, right? So that's going to be 10 to the negative 3 molar. Well, that looks kind of stupid like that, just saying. So most people write it as 1 times 10 to the negative 3 molar. So the exponent, the pH tells you the exponent for the hydronium. So that's like the log logic rule. That's my lingo in there, but that's what I'm talking about. And that's a lot bigger number than like part C. Part C's concentration of hydronium would be 1 times 10 to the negative 10th. That's a lot smaller. Well, that makes sense. pH 10, is that acidic or basic? pH 10. That's basic, right? We should have very few hydroniums than we do in the negative 10th. Versus pH 3, which is acidic, we should have a lot of hydroniums, and that's what we do. We have 10 to the negative 3rd. Okay, do you guys, let's see here. We have about 30 minutes left. I have 2 things. I want to take our Socrative quiz. You have your reading guide 19. I'll leave it open reading guide. Open reading guide. Heck, I'll leave it open little book. Open notes, okay? It's really simple. I just want to make sure you're okay with the definitions. Those are the ones that I think will bite you in the butt if you don't know your stuff. And after that, we continue working on PS19B until I tell you what we're going to do after that, because I'm going to see if we're going to actually do our notes or not.